You type a logic puzzle into an AI prompt, hit enter, and in a fraction of a second, the screen fills with a reasoned answer. That speed makes it hard to tell what occurs inside. Computer scientists have debated whether these models reason through problems, or if they act as a sophisticated, pattern-matching autocomplete. The problem is that neural networks are largely black boxes. We write the initial prompt, and we read the final text on our screen, but the billions of intermediate calculations bridging the two are opaque. Because human observation is limited to the final output, science has lacked the evidence to confirm if an AI possesses an internal thought process. Researchers at Anthropic recently developed a mathematical tool called the Jacobian lens, or J-lens. This diagram represents an AI's network layers. By isolating a single internal node, the J-lens measures the exact vocabulary words the model is poised to say at any specific microsecond of its internal processing. By using this tool to read unspoken words, researchers mapped the structural anatomy of an AI's thought process. We can now follow a prompt directly into the machine. If we travel chronologically through the physical depth of a transformer network, our journey starts immediately after the input layer. These early layers act as the shallows. Here, the network is dominated by automatic, parallel processing. The model handles mechanical tasks in this phase, like keeping track of character counts, parsing basic grammar, and formatting data. While this processing is vital for the AI to function, it operates without active focus or flexible reasoning, similar to the human brain's unconscious reflexes. Deeper into the middle layers of the network, the J-lens detects a shift in how data is handled. This network diagram shows thousands of parallel data streams compressing down into a single, tightly constrained central bottleneck. Researchers call this the global workspace, or J-space, the site of flexible thought. The workspace holds a single concept and broadcasts it to solve novel problems. To test this, researchers asked the AI to solve a multi-step math equation, 4 plus 17 times 2 plus 7. This timeline graph maps the AI's processing stages. The J-lens catches the AI silently holding the intermediate numbers 21 and 42 in the workspace before it ever generates the final answer. In another test, researchers fed the AI a prompt containing a deceptive hidden injection attack. Looking back at the timeline, a new hidden spike registers. The J-lens detects the words fake and injection lighting up internally, confirming the model is recognizing the trap in silence. The global workspace provides evidence that AI performs scratchpad math and identifies traps in an internal monologue long before it ever moves its mouth. Finally, we reach the motor layer of the AI. Here, the internal deliberations of the workspace are translated into the visible text typed onto the user's screen. This two-part architecture introduces a significant risk. An AI is capable of silently panicking, strategizing, or deceiving within its global workspace without ever typing a suspicious word. The J-lens changes AI safety by providing a way to monitor the workspace for malicious thoughts as they form. Assessing an intelligence based solely on its words leaves its underlying intentions unmonitored. Researchers are now applying this discovery through a technique called counterfactual reflection training. This schematic shows the middle layer workspace nodes being linked to a prominent ethics node. This implants ethical concepts into the global workspace during the AI's silent reasoning phase. Models trained this way change how they deliberate in silence. Their behavior improves without needing to be trained on the final text output. The J-lens has opened a window into the silent reasoning of artificial intelligence, allowing us to see, measure, and shape thoughts before they are ever spoken.